All right, so today we're going to talk about distribution infrastructure, and yeah, there's going to be a little bit of overlap with some of the stuff that we talked about last time, but I think some redundancy is useful. But we'll also get into some aspects of the infrastructure that's going to look a little bit different. Okay, and so we've been talking about kind of how we move our electricity, right, from the generators to our end use, and we've talked about kind of the components of our power system. We've covered generation, we've covered transmission, and so today we're going to mainly focus on the distribution infrastructure, of which, yeah, you guys are going to have a chance to see up in person on Thursday. So, yeah, the first thing I want to talk about is topology. And so, again, kind of reiterating what was covered in the sort of guest lecture, right? When we think about what is the distribution as it pertains to like the poles and wires going to our end uses, right? This is everything in the system following a transformation step down from our transmission system to a lower voltage, and then going all the way to our sort of end use customers. When we do this step down, there's commonly kind of multiple levels of voltages on the distribution system. And a lot of folks typically divide this into what's known as a primary distribution and secondary distribution. And the easiest way to think about this is the primary typically is kind of your higher voltage in the distribution, and then the secondary is kind of your lower voltage section. Okay, and so we talked about how, at UC Davis, they use a 12,000 volt system, and that can vary in the primary distribution. It can be as high as 34,000 volts. That's common in like the Los Angeles area. And from the sort of high voltage distribution system, you might go down to kind of a medium voltage distribution substation. It's not always the case that you'll kind of be dropping down to here, but generally we will have our secondary distribution where we will go down to kind of the lower voltages that we're kind of used to at the end use. Okay, and so 120, 240, 480, these are kind of common voltages at the sort of customer level. And just if you kind of imagine the whole schema, right? We in our electricity system, we are moving from 100,000 plus volts at the transmission level down to tens of thousands of volts or thousands of volts in our distribution system, down into the kind of hundreds of volts that we end up using. All right. And so distribution network is meant to bring electricity from those substations right to our end use customers. All right, so thinking about sort of the topology, or in other words, the way in which the wires are kind of set up in the network, what are some of the ways that this happens, or that they're kind of laid out, right? And so kind of the most common example of topology is radial network. It's kind of the simplest. It's also definitely the cheapest and easy to design. So essentially what you have here is the sort of notation for this network. The sort of brownish reddish is going to be your high voltage transmission, and then you have a substation. The two rings essentially denote transformation down to a lower voltage. Green, we have our primary distribution, and blue is secondary distribution. So you have another set of transformers here to drop in voltage from primary to secondary. All right, and so in the primary, you kind of run a line, and off of that line, you essentially have this sort of radial network where that distribution line, what we'll call, right, a feeder, goes out to connect to these secondary lines that are kind of separate. Okay, any questions about kind of this layout here? So a different way that you can lay this out is through a ring or a loop configuration. And so this is what we heard about how much of the system is set up on campus, right? And so this provides a higher sort of reliability, right? Because if you think about, you know, what happens if one of the sections fails, you can still provide electricity by going through on the other side. So these systems or these networks tend to be a little bit more complex and a little bit more costly. Yeah, and then depending on kind of the layout and configuration, not everything can really be sort of energized simultaneously. So you're actually running certain like open and closed configurations on the loop to make everything work. But the redundancy is there so that if you have a point of failure, you can always come in from the other side. Okay? The X's in this case are switches that you can open and close. Yeah, and then you can also run in parallel. So this is where you might have sort of multiple transformers feeding a secondary system. Typically, highest reliability, you might have more redundant paths, and so it's better for voltage regulation as well. But it does require kind of phase matching between sort of multiple transformers that are coming into different feeder lines.
To the right on that, is that like transmission coming in?
Yes.
Okay.
Yeah, so the brown red is high voltage transmission, and then the rings are representing essentially the transformers at a substation to drop you in voltage. Yeah.
We might have gone over this last week, but could you just repeat what phase matching entails again?
Okay, yeah, so we don't get too much into like the power flow here, but one of the aspects about AC power, right, is that it's going in kind of this sinusoidal wave. And so one of the features of that is that actually in an interconnected electricity system, everything has to operate in sync with that wave, okay? And so you can imagine, you know, the electricity going through that feeder is essentially propagating with a particular frequency in sync with kind of the rest of the electricity grid. And you cannot actually have like multiple lines that would be operating even in the same frequency but out of sync. That, yeah, physically would not work. You would end up, yeah, depending on where you are in the system, blowing lots of things, damaging equipment. It's one of the reasons why at the sort of transmission level, we think about the grid in the US as partitioned into three main areas. There's WEC, ERCOT, and the Eastern Interconnect. And one of the reasons why they're left kind of separated is because even though they all operate at 60 hertz, actually they're not in sync. And in order to get them in sync, you need to have like a you need to transform your AC into DC and back into AC to have like what's called a DC tie. Yeah, and all of that has to do with this phase question of making sure that the waveforms are in sync. Yeah, does that?
Yeah, no,
Yeah.
it's kind of, I remember.
Yes.
Is it possible for multiple areas of a grid to be like in slightly different phases? Like, I mean, well, I guess if you have a single source of transmission, as electricity moves on, does the phase lag?
It's kind of an interesting, way of asking it, but I mean, I would think the way that you would think of it is like it's all like one big wave that goes all the way through an entire line. So no matter how long it is, you can't have it be discontinuous at any point as it's moving through.
Right.
So no, not really.
Kind of
And
like a standing wave.
yeah, and the it's electrons moving through at basically light speed, right? And so the distance part of it is, I mean, even over tremendous distances, this stuff is going to be, it's not really going to make that much of a difference. Yeah. Okay, any other questions? Cool. So we saw, some schematics of the UC Davis system. Thought it might be interesting to look at the city of Davis as well. So the UC Davis substation is located over here, which we'll visit in a couple days. The city of Davis has a substation owned by PG&E that's located right over here. This is on L between like 4th down to 1st or 5th down to 2nd Street. And so that substation essentially imports the electricity off of the transmission system to provide to the rest of the city. And here you can see kind of roughly what those feeders look like. And so I believe the city of Davis is configured in like a standard kind of radial network. And so, you can see kind of these configurations in other IOU territories as well. So actually this data is public. It was required to be public by the PUC in like the mid 2010s in order to help with DER developers. And so researchers can actually take advantage of that and kind of do deeper investigations of the distribution infrastructure. A lot of my work involves looking at this as it relates to like capacities for adding like EVs to the grid, for example. But this gives a rough sense of some of the feeder line topology in different areas in California. And yeah.
I guess I was just kind of curious, so you said a lot of these are radial networks, do they ever make allowances for like parallel or circular segments for like hospitals?
Yes, absolutely, yeah. So, those configurations, it's not like one utility does one thing and one utility does something else. The demand for particular configurations is based on reliability needs and sort of cost trade-offs. And so certainly, for something like a hospital or any infrastructure that requires like a critical reliability for electricity, oftentimes you will find that the design of the distribution system for those end-use needs might be different, right? They might be operating in with a series of loops or in these sort of parallel configurations. Yeah. Any other questions? Yeah, and so just to give kind of a higher level sense, this stuff is spread out everywhere, right? Essentially, if you want to have electricity, you're probably sort of interconnected with the network in some way. And this shows the colors of all of these kind of sprawled out lines kind of correspond to connection to specific substations, which are represented as black dots. And generally, the larger the size of the black dot, kind of the larger the sort of total capacity is of electricity they're serving, yeah.
So each of these colored networks would be distribution networks, or?
Yes,
Okay.
this is all at the distribution level. Yeah, the transmission network is going to look a little bit different, but you can imagine essentially that the transmission network that moves through this area essentially has to go and connect to all of these black dots, right? Which then propagate out the electricity to your end customers, right? And so the colored sort of network here brings electricity from the substation to your customers, and then the transmission network brings electricity from the power plants to these substations. Right. Any other questions? Great, okay, so let's talk about the sort of physical components of our distribution network. Okay, so I'm sure you guys are pretty familiar with these. Everyone's seen overhead lines before. Yes. Yeah, and so an individual feeder line, can be serving thousands of customers, and most distribution networks are built out, using these overhead lines, right? So this accounts for like over 70% of the sort of total miles in terms of the circuitry built out for the distribution systems. We don't see many overhead lines on campus, right? And actually, depending on where you are in Davis, you might not see these either. In the area that I live, for example, there aren't any overhead lines in my neighborhood, but in some of the older neighborhoods, you do see them. And so if you get electricity, but you don't see these sort of overhead lines, that means that instead those lines have been buried underground, right? And so underground lines have higher reliability, but the sort of maintenance and repair costs and actually the sort of deployment of these things are a lot more expensive. So we did talk, right, about undergrounding in transmission systems, and we looked at some of those costs being about sort of 10x higher. And kind of the same is true for distribution. You can imagine that putting up a pole versus doing this kind of trenching has fairly different construction costs. So they use conductor for the wiring, right? And so there's similar to the sort of transmission system, different materials and configurations. Usually you've got some aluminum and copper type conductors that are meant to sort of convey that electricity over the sort of distribution distances. Okay, in overhead lines, you might have something like multiple voltages running through, and so the top ones are going to be the higher voltage, so that's your 12 kV, and then you might have older sort of legacy lines running at 4,000-ish volts, and then the stuff typically at the bottom could be like legacy telecom stuff or telecom wires, so not for power. So oftentimes overhead lines are going to share utilization with other utility services. Okay. Yeah.
Just to make sure, by legacy, you mean like sort of a, I guess, older system, but still maintained?
Yeah, so an example of this might be in a territory that was sort of developed. Originally, they had sort of 4,000 kV lines running through it to, you know, maybe provide power to a particular neighborhood or, you know, commercial area. And then maybe the city expanded and grew, and they wanted to sort of add capacity, electrical capacity. And so what you can do is maybe add in, you know, 12 kV lines that would provide additional electricity capacity, to serve a growing sort of end user base. And so oftentimes you see stuff like this happening. Okay, so who's seen one of these guys before up on the poles? Yeah, so these are pole mounted transformers, these like bucket type things. And right, the transformer, so these pole mounted transformers are kind of the last step to bring down the voltages to kind of the types of voltages that we would expect out of you know, a socket like this. Okay, and so as we talked about last week, one of the limiting factors for these transformers is its thermal rating, right? If these things get too hot, you can have damage that sort of degrades the transformer. That could put it out of commission, or in more extreme cases, you know, render it inoperable, although there's a lot of sort of protections against that. And so thermally, you want to provide some protections. These guys typically are going to be sort of passively cooled. They're filled with mineral oil, and so in a typical day cycle at night, these things will help cool down the transformers after like a day's operation. Yeah, a single 25 kVA transformer might serve something on the order of like 3 to 5 homes, depending on the load in those homes. And you can imagine that as we have this sort of transition to more electrification, right? So that could be heat pumps, electric vehicles, electric stoves, right? These numbers might start to be on the low end, and so the high end you might need upgrades to transformers to kind of deal with newer sets of electrifications that are pushing the demand higher than kind of the original anticipated deployment of these things and what they were meant to serve. So that's a common problem that, you know, we'll kind of touch on throughout class. Okay, we also have pad-mounted transformers. And those can be similar in function to the pole-mounted transformers. Oftentimes you have a little bit higher capacities for those guys. Yeah, so transformers, typically the voltage in, depending on you know, where you are and the type of voltages that are on our sort of primary voltage levels in our distribution system. That ranges from 4 to up to 34,000 kilovolts. And we get out of that, right, the things that we're kind of used to. Yeah, 120, 240, 120, 208, and then the 480 volts. All right, any questions? Okay, a lot of the hardware that we're gonna kind of touch on now, and that you might kind of see out in the wilderness, are really meant to create more reliability and resilience in our distribution system, right? Because actually, when you think about what's required to just serve the electricity, you don't need much more than the wires and the transformers. But to make it resilient to, you know, certain things that could interrupt your sort of power flow, you might add in a lot more other types of equipment that can help with particular sort of issues in the distribution system. Okay, so one thing that is common to see, so voltage regulators. So voltage can drop as a result of kind of moving through the wires, right? This is due to impedance. We're not really going to talk too much about that, but basically as electricity travels through wires, you're essentially experiencing these voltage drops. And regulators are ways in which you can essentially boost the voltage back up. And that's a useful feature in order to maintain, some of the power quality in our distribution system, but actually are also one of the areas that that start to become a little problematic when you have a lot of DER and distributed solar feeding electricity back into the system. And we'll talk about that more in just a second. Other things to help with power quality, so capacitor banks to supply reactive power. And these can change in the way that they're utilized depending on the season, because it actually affects power factor issues. So if you recall from the last, the guest lecture, there is a difference between the way we talk about ratings on transformers in kVA as opposed to kilowatts, and that's a difference by power factor. And so if a power factor is 1, then kVA and kilowatts are the same. But for a transformer, it doesn't actually care about kind of the power that you're using to generate useful work at the end. It just cares about the kind of the current going through it, which is why we have this power factor that you have to think about. The closest kind of analogy that you can think about this is kind of like if you have a box that you're trying to push along the floor, right? If you push perfectly laterally with the floor, then all of the work that you're doing is transferred into motion. But if you push downwards at an angle, some of that work that you're doing is essentially getting lost, because any force that you're going down is kind of lost, is kind of like wasted energy. And so the analogy here is kind of the power factor essentially describes how much useful work that you're able to extract out of the electricity. In a very sort of analogous way. All right. So what type of other protection equipment is out there? So the simplest is a fuse. So if something happens on your line that could cause maybe a surge in current, one way to protect the equipment is to have a fuse. And essentially a fuse is kind of like a single-use item. It's going to essentially blow, and then you need maintenance workers to come in manually to replace it, okay? And so the actual equipment cost is very cheap, but the maintenance period could be costly and also long, right? If you have a system that operates entirely on fuses, you need someone to come out and essentially replace it. Yeah, and so fuses are a common sort of protection equipment because they're so cheap and easy to deploy. But you might use something a little bit more sophisticated, such as a recloser. Okay, and so a recloser is kind of like a circuit breaker. So it will essentially open the circuit when you have some kind of fault that you want to deal with. And so, like a fuse, it's going to activate under certain conditions. We'll open the circuit, but then it's going to try and close the circuit again to clear what might be termed like a temporary fault, right? Yeah.
Is that like something's out of phase or?
So it could be, but more commonly, it could be something like a tree falls onto the wire and like grounds the electricity, right? So now you have all this current that's like wants to go to ground. And so with a fuse, it would blow, disconnect it so that you don't run into that issue. With a recloser, one thing that could happen is, let's say you have a tree that falls over temporarily, like touches that line, and then normally it would blow, but then you open the circuit with the recloser. Now, if that tree stays connected to the wire and is like grounded, what ends up happening is, well, let me go the other way. If the tree hits the line and then falls over and is no longer touching the line, when the recloser closes the circuit again, let's say everything is good, and then it stays closed because you're not experiencing this like surge in current, right? And so your fault has been cleared. But if the tree stays up against that wire and provides a path to ground, and essentially is causing this like overload in your system where it wants to draw a bunch of current through, the recloser will see that happening and open again. And so it's gonna try a couple of times and say, oh, actually there's something wrong in my circuit downstream, and so I'm gonna stay open. And so this is a nice thing because temporary faults can get cleared, and then you don't need to send out a maintenance worker like you would to replace a fuse. Okay.
Sounds like it's an amperage-based system, mechanism.
Yeah, it's basically like a circuit breaker. Yeah. The sectionalizers are the equipment that are working kind of with the recloser. These are the things that actually will technically count how many times the reclosers are opening and closing. And once it reaches a threshold, it tells the recloser basically, hey, stay open. Okay, you've tried to clear the fault enough times, and it's not doing anything, so stay open. Yeah, so these systems are usually coupled together. Yeah, and so as was kind of discussed last time, squirrels, birds are responsible for, a significant fraction of distribution faults, right? Either connecting two lines together or connecting the lines to ground. All of those are going to cause big problems because essentially you're going to have all this electricity that kind of wants to go to an unintended path.
We have a lot of squirrels on campus.
Yes, And what was the the number again? You recall for how much that how often that happens here?
That's squirrel related.
Yeah,
I don't remember.
it was a lot. Yeah.
Yeah. I think most outages are wildlife related.
Yeah.
Here.
So, you know, utilities, there are a number of things that can cause these issues, right? There can be weather-related events that could, you know, maybe if you have high enough winds that they are knocking things into your lines, or even, this is a lot rarer, it's usually in more degraded lines, but if there's enough droop in the lines, they may actually swing the lines together, right? So things like that happen. But a lot of those things, except in kind of more extreme cases, can get dealt with through like good maintenance, right? And so think about like trees and branches like falling onto the lines. Well, if I clear, if I do vegetation clearing, you know, that can help with that. If I make sure that I don't have like sag in the lines, right? If they're starting to degrade, you know, you'll make sure that like even in higher wind events that they're not like blowing into things. But I guess with wildlife, unless you like, I don't know, exterminate the squirrel population, you're not really going to be able to solve all of these issues.
For the wildlife protection devices, are like anti-perching, like what are the?
Yeah, things like that.
Spike strips and maybe things that roll.
Yeah, those all kind of make sense to me. I can't say I'm quite like an expert in that area, but yeah, those types of measures I would imagine are pretty common to try and mitigate some of this. Yeah, like if you look at some of those utility poles, they often have, you know, the spikes to make sure that like birds aren't like nesting on them and that sort of thing. Although I have seen some nests on some of these utility poles before, so not always successful.
If you have an outage and it like goes out and comes back on,
Uh-huh.
comes back out again, it's probably a reclose.
It's probably a recloser, yeah,
So like
yep.
It's waiting, if there's a fault, it tries again.
Yep.
If there's still a fault, it opens back up.
Yep, and you'll see the power like in your, you know, house or apartment will come on, go off, something like that.
But if it stays on, it likely means that like something got fried and then it like opened.
Yep.
And it closed.
Yeah, yeah,
Fault is
exactly.
clear.
Yes, yeah. Hopefully it was like, it was just like a branch that like
Yeah,
did a
it could
quick
be a
short,
branch, yeah.
right? Yeah. Hopefully it wasn't, well, it could be a squirrel that got also shorted, yeah.
I have a quick question that might be semantics. So when you say that like a recloser helps clear a fault, would it be more accurate to say that the recloser waits for the fault to be cleared?
Yeah,
'Cause
well, it's like,
What is the recloser actually doing to solve the problem except for just shut down that line to avoid further damage?
well, exactly that, right? So what can end up happening is, something, when you have something shorting the line, right, you could be sending an enormous amount of current like maxed out through those lines, which would be damaging the lines, and if there's equipment in between that, could be damaging those equipment too. And so you open up the circuit to keep that current from reaching the equipment and sort of damaging it, with the hope that whatever happened downstream that caused this sort of oversurge of current, you know, is fried away, falls down, whatever. And so when the recloser closes again, you go back to normal. if that makes sense. So like, it's not like the recloser physically is fixing the problem
Yeah.
downstream. Yeah, the hope is that the problem downstream is a temporary one, so that by the time you've kind of opened and closed the thing again, you, the fault is cleared and that you're not damaging your equipment.
Why would equipment be damaged?
Yeah, so, okay, imagine that, imagine there's a transformer in between, imagine there's a transformer kind of in between where this is happening, right? And you send all that current through the transformer. It's like, maybe it's more than its rated capacity, and then you like melt so they talked about how you have these like paper insulation in between the coils. You melt away that paper and you blow the transformer. And now the utility's gotta come out, replace that transformer. You've got a blackout in that whatever services being, or whatever customers are being served electricity from that particular transformer, right? As opposed to here, recloser opens, stops the current from blowing that transformer. Now the utility doesn't need to come out and replace that equipment, which is gonna be a lot more expensive, right?
Could have a long lead time.
Yeah, and so that blackout could be like many hours, many days, right, for utility to come out and replace. So this stuff helps prevent that, right? And so Fuse is kind of like the simple version of that, where yes, someone will still need to come out, but at least it's faster and less costly than replacing a transformer. And then with the recloser, hopefully you can automate some of that away. Yeah.
And just to like reconfirm, the sectionalizer like helps detect if there's a fault and then informs the recloser like on what to do.
Yeah, so the sectionalizer literally counts the number of times the recloser is opening and closing, and it basically says, oh, if you, I think the rule is 4. If you open and close 4 times, usually, it will tell the recloser to essentially stay open.
And the recloser, would like the one be opening and closing be upstream of the fault or downstream? Like how does it detect?
Upstream.
Okay.
Yeah, because downstream, you're already too late, right? Whatever's happening up there may not even reach you. Yeah.
So how does it like detect that there is like an issue?
Yeah, so so the physics of it, I think it's, it literally looks at the amount of current passing through. And so, yeah, I don't imagine that it's the same as like a circuit breaker, but we did talk about this, right? So with a circuit breaker, there's actually a physical deformation as the metal heats up if you have too much electricity passing through, and then that actually caused that physical deformation opens the circuit. I don't think they do that here.
Yeah, because if it's like
But-
upstream of the fault, then like what would, cause it to respond, I guess, like that, for it to, if it's trying to detect something that's happening downstream and closing it beforehand.
Oh, yeah.
You know.
So what happens when you short or ground? You basically, all of the electricity in the wire wants to go through, so it's like sucking up a giant amount of current. So everything upstream of that is gonna see this huge like rush, or I don't know if rush is the right sort of verb to describe it, but it's going to have a big sudden increase in current.
Okay, thanks.
Yeah,
Like a water leak.
yeah, exactly. Yes.
Aren't power lines protected with insulators, so like a bird or something lands on it, it's not gonna get fried and cause.
Yeah. So insulator. So what is an insulator? It's something that electricity does not want to travel through. Okay, and so air, for example, is a pretty good insulator. But actually, imagine you have like 2 lines, right, and then they like get a little bit closer together. Actually, at some point, right, electricity wants to go down the path of least resistance, and so usually it doesn't want to go through insulators. either the air or the thing that is encasing it, right? But, you know, imagine that you're in like a transmission line, right? You're extremely high pressure, you know, high voltage, so I'm saying high pressure, right? The water analogy. So, but you've got to travel down this pipe like many, like hundreds of miles or something, right? Is the path of least resistance going to be going that long distance, or, you know, if something gets close enough, you know, you're actually going to be like, oh, I'm going to go through this insulator because actually now I have this path that's going to connect me to close this circuit right on the other line. So insulators are a barrier to prevent electricity, but they're not like a, you know, total failsafe. So if I have two insulated wires that have high voltage electricity, and I like grab them, right, and close a circuit, that electricity may want to travel through me, then go all the distance down to wherever it needs to go.
So it can go through.
Yeah, exactly. And that's like, even, you know, if things get close enough, you can get like arcing even through the air, right? So even air, which we typically think of as like a really good insulator, you can get like arcing if that path is looks more preferable for electricity to travel through. Yeah.
So, I don't know, a tree falls on a line or whatever and shorts at the ground.
Yep.
I'm not sure I understand why the current was surged because of that.
Yeah, so think about the electricity that is going through that line that might be serving this neighborhood and this neighborhood and this neighborhood. It is all of that electricity is now going through this like one path, right? And so,
Okay.
yeah, that's essentially, yeah.
It's like the little Dutch boy, his hand, his thumb and
I don't know this.
yeah.
No.
Yeah, like you have a bunch of water behind a dam, and now you're just spraying a hole in the dam.
Mm.
It's not gonna wanna stay, it's not gonna go through the hole.
Yeah.
So, which one does either voltage or current is demanded, right? Like you demand current and you simply get whatever voltage is coming through, right?
Yes. So, right. So going back to our water analogy, right? Current is like the quantity of water. Voltage is the pressure. So whatever voltage is in the system is kind of like the pressure that you're going to see if you know, tap into a particular spot at that voltage. Okay. Yeah, so a lot of this stuff, a lot of this equipment, you know, can help with not necessarily the day-to-day operations, but with reducing costs and maintenance, and not just cost, but like the timeliness with which you can recover from like a blackout event or, you know, some kind of fault event. Okay, and so, you know, as we work our way through the distribution network, you know, you step down at these transformers and then you go through these lines to eventually serve your end-use customer. The way in which we measure how much electricity is used, right, I'm sure you guys have all seen these before, are meters. And so coming in from the utility lines and then going into kind of the customer, into the sort of customer end use, you've got this meter that kind of sits right at that intersection, which essentially is going to measure how much electricity is passing from those lines into your sort of ultimate end use consumption. Yeah, so nowadays, particularly in like California, you're gonna see more of these types of meters where you see there's a lot of information that's kind of reported. these are called smart meters, and they report usage on a fairly rapid basis. And they're even equipped to be able to detect certain sort of anomalies and outages and that sort of thing, and be able to report that back to the utility. These are, I guess, a little bit more modern. So in the sort of, I say olden days, and by olden days I mean, I would say, 15, 20 years ago, when these were first starting to get rolled out, most people had, I guess, what you would call dumb meters. So these are meters that would still read the amount of electricity being used, but then you actually literally had to have people go out and read the meters in order to estimate how much electricity that you were using. And so back in those days, yeah, the amount of money that you get charged by utility is actually more based on estimation, and they do these like true ups when they read the meters. And that might be happening like once a year. So now we get much more sort of accurate transmission of information, which, yeah, I think generally is a good thing. I'll also note that these meters can kind of run backwards. In other words, if you are injecting energy into the grid, the meter will go in the opposite direction and be able to count essentially what you are contributing. And so that's called net metering. And that's going to be kind of an important concept, particularly in California. And why is that?
Selling electricity to the grid.
And how would you be selling electricity? You have a power plant in your backyard?
I have solar panels.
Yes, all right, so solar panels, right? So solar panels on our rooftops is, yeah, a pretty different way than we've traditionally done power generation, right? Our electricity system has traditionally been big power plants produce electricity, we send that through a transmission system, through a distribution network to us, whereas this sort of what we call distributed energy resources, which are things like solar rooftops, now you're producing electricity kind of at the location that you're using. And so if you send electricity back onto the grid, then you need to be able to kind of count that as well. And so that's going to be a pretty important concept to think about for things that the grid is going to have to deal with in the future. Okay, so this is a good point to maybe take a quick break. So let's do let's say 4-minute break, and we'll reconvene at 4:11.
Those smart meters also stop unscrupulous people. My uncle told me about something although I don't know if he did it or I won't implicate it, but he said more or less.
I don't think we're.
You can take the lock off and then take the meter out and flip it around on the old ones, then it'll run the meter backwards when you use power. And so if you got paid
Really? That's
for the
crazy.
parties that he would throw.
Wow.
Yeah, he said he'd do it when he would throw large parties. Now I have a
I feel like you could get in pretty big trouble for doing something like that.
Yeah, so he is a journeyman electrician.
Yeah.
He had the correct things and then be able to reconnect.
Yeah, there are things with like utility services and like, like certain taxes on services that people try and game that like, I feel like the government comes down pretty hard on stuff like that.
Family member will say.
Yeah.
I think we should tell him to retake the ethics part of his
Yeah.
He's an interesting, he's retired now. He's an interesting.
No offense.
No,
Yeah.
no offense, for sure.
Or his license, a license, or.
Yeah, he's no longer working, but,
I'm guessing there's something in the licensing process in which you say you will not do such things.
Yep. Yep.
Yeah, but you can say a lot of things.
not condoning it, just, smart meters are great.
Yeah. I mean, there's still some like holdouts, I think, that are like really anti, there's a like a privacy aspect, Big Brother aspect to this that yeah, it's
I think LADWP,
they still have, yeah,
1990.
yeah.
I could be wrong.
And
They're
yeah,
doing it, they're doing it now.
it's tough sometimes to like convince some folks to transition, but yeah, I don't know. It's a little silly to me. These things are like make life so much easier for everybody. Huh?
I was just trying to.
No. You still don't understand that, the short thing?
No, I need like diagrams and drawings, because I don't understand all this talk about, well,
Yeah.
I don't know, I await revelation.
I think that the wires, I'm not an electrical engineer, but the wires have a capacity. It's like a pipe, right?
Yeah.
With a certain diameter. And that's determined by the resistance within the wire. It can only convey, for that voltage and that wire size and that wire material, it's going to convey a certain amount of current.
Mm-hmm.
And it's just gonna convey that, right? I believe.
That's right. And so when you
Transmitting all that voltage, all that current.
No,
Well-
that's like businesses, that's like it's working properly. It's transmitting a certain amount of current for the voltage, the wire size, and the wire material.
yeah,
Then all of a sudden, you created an alternate path for the electricity that allows as much current as it wants to go into the ground. Like
Yeah.
if you touch this, that current could go through there at a specific, it's gonna have a specific current going through that wire, or it could go through my hand into the ground.
With a lot less resistance.
With a lot less as much current as it wants.
Yeah.
Why isn't that
Determined by the
less
voltage.
resistance though? Wouldn't the power
So,
dissipation for your
well,
voltage-
so let me maybe give you an example that might help. So, say you have a wire, say you have a circuit in your home that is hooked up to a set of wall outlets, and let's say it's got, you hook it up to like 20 wall outlets. Put a blow dryer in, right? Uses a lot of electricity. And then you put a toaster in, and then you put a microwave in, and you run all this stuff, and you just like keep putting more and more stuff in. What happens at your house when you do that?
One of the breakers flip because
Yep.
I'm asking for too much current.
Yeah, so you're asking for too much current. And the circuit will trip, the circuit breaker trips in order to protect bad things from happening. And so what are the bad things that might happen? So now imagine that you don't have a circuit breaker and that it's just straight up connected through, your, I don't know what gauge wire it would be, but like a 12, 14 gauge wire. Okay, so now you no longer have protection and you start plugging all these things in. What do you guys think happens? So there's no longer a protection against putting too much current through that wire. The wire is actually rated to be able to handle some amount of current. But it doesn't mean that you can't send more current that's rated through it. You just continue to pile on, and the wire starts getting hotter and hotter and hotter until, okay, you likely will cause a fire because it gets so hot that the insulator melts and things that circuit is like connected to, like in your house, will start like catching on fire. But what ends up happening to the wire itself is it actually deforms, and then it starts to like melt, and so that's a really bad thing, right? Because now you have, because you don't have protection and you're just asking for all this current, you damage like the wire itself. And if that wire is going through other things like light switches or other circuitry, all that stuff is going to get harmed by all the current like passing through this wire. So it's a very similar thing that would be happening at a different scale, right? If you don't have protection, like that circuit breaker in your distribution system, and now you're asking for all this current, right? You're plugging in blow dryer, microwave, toaster, another blow dryer, whatever. That's like the equivalent of sending something to ground. It's like the ground it's gonna say, I can take all this current, like just keep giving it to me as much as you can, and all of that going through your wire
Okay.
will, yeah.
I think that was where I was confused, because it wasn't clear why the ground would be the equivalent toaster.
Yep. So yeah, we call it ground. Well, I guess because it's literally the ground, but the ground will soak up and take an infinite amount of current. Well, essentially infinite. Yeah.
Taking the time,
Yes. Okay. Oh, we got to get a move on. All right. So, distribution load characteristics. The main point of this slide is mainly to show that, like, you know, and this should be hopefully kind of obvious, but that sort of load profiles, you know, they're not this flat thing that happens throughout the day, right? We use and desire electricity in sort of different magnitudes across the span of a day, and so you might have different sort of shapes. But you can imagine that the load profile that a particular, you know, distribution feeder and the equipment corresponding to it may see could be very different, right? You can imagine, like, do you think that the sort of transformers and the circuits on UC Davis campus looks the same as the one in your neighborhood? Probably not, right? You know, people use electricity more during the day here, whereas maybe you're using electricity more at your residence at night, right? And so there's different sort of profiles, load profiles and characteristics that we talk about, and that can lead to particular sort of design elements of your distribution system. And that can also change over time as well, which is, you know, one of the things that might be a challenge, right? Maybe I've designed the sort of layout and build out a specific infrastructure on my distribution network to handle a particular type of load profile, but now suddenly everyone's driving electric vehicles and you have big load spikes at night, which it wasn't designed to sort of handle. So the load shapes of these things and the sort of corresponding implications on the distribution system are going to be an important thing to kind of consider. They also change temporally, right, depending on day and season, to say nothing of these like larger scale transitions. Okay. So related to this point that we've been kind of skirting around, the equipment in a network, both the wires and the things like the transformers themselves, have like ratings and sort of maximum amount of what we call sort of hosting capacity, right? That they can handle. So you want to make sure that your voltages are kind of within a particular range, and things are rated in such a way that, oh, I as a transformer am sitting at this particular location and I expect a certain amount of voltage going in and kind of coming out, right? And so when you think about the design and the sort of deployment of particular types of transformers, they're all done with this in mind. And when you have certain things that affect those, that's when you start running into trouble. So the transformers and conductors will have thermal capacity limits, right? And so this is what happens if I send too much current without any protection through a conductor or through a transformer. That's when you start damaging things, right? If things get too hot, wires themselves can degrade, the transformers themselves can get damaged. And so thermal capacity is an important thing to keep in mind both as a precaution against degradation, but also to like literally keep it physically operating. Hosting capacity is kind of the maximum amount of capacity a circuit can handle that you can get to without triggering some kind of like voltage protection or thermal limit. Sometimes the kind of thermal capacity itself might be set at kind of a lower level than the hosting capacity. What was that?
Something's crackling.
Okay, something shorting. Yeah, and so that thermal limit, maybe you are physically able to, heat up a wire or a transformer a little bit, and that's okay, but you don't want to like keep violating it. But with the hosting capacity, you hit that limit, and then things start, like protections start triggering, right? And so this might be, let's say, like a harder limit than your thermal capacity. Okay, so, how is a distribution network built out? I kind of think of this deployment across several phases, right? And so there's some kind of trigger or event, right, that is essentially like, hey, I need more electricity in this particular location, right? So maybe you have a new sort of neighborhood getting built up, or we have, let's say, a new campus building getting built up, and you need electrical capacity to serve it. And so you make this large load request, and then, and also in some cases, maybe you want to build solar on your rooftop. You might need to make an interconnection request there. And so there are a number of things that can kind of trigger the start of this sort of build out or deployment. You need an engineering assessment, and so they're going to look at all of this stuff about, how much load do you need, how big of these transformers, and how many of them do we need, right? And so there's a number of things that get assessed in order to make sure that when I build out the distribution system, it's not just like willy-nilly, right? I am sizing the system to be sort of like economically efficient, and that I'm serving a particular demand that I know is going to be there. And that can be tricky, right? These things may also sort of change over time, and so to what degree am I kind of future-proofing versus just serving kind of the immediate load that I know is going to be there. You're going to design the system, so once you know about all of this stuff in the design, you're going to have to make some decisions about, is it going to be overhead? Is it going to be underground? Am I going to tap into a particular feeder, and where is that going to happen? And so system design, engineering, and assessment kind of go hand in hand. And then there's the actual sort of build out of this stuff, right? And so that means the utility, who's the one the entity that's typically going to be the one building this stuff out, they are going to have to coordinate with whatever land use requirements are there and rules. Maybe that's at the city level or the county level. You're going to have to do permitting of all kinds, and then you got to like procure the materials that you need, do the construction, and then and the final step is the actual energization. And so energization is everything's in place, everything's connected. Now let's like open up the pipes and send the electricity through. And that's kind of your kind of final step. Okay, and so what is the kind of utility responsible for in the build out of this stuff versus what are the things that the end user is responsible for? So this is a nice little graphic that I found. So everything in green is the responsibility of the utility, And then for this residential service, all the stuff in black is the homeowner's responsibility, so for, yeah, residential. And so the utility is going to essentially create a service drop, right? Which will essentially provide a connection to the transformer on the secondary distribution voltage level to provide, you know, whatever you need at your house. There's gonna be a connection point, and then the only thing that they're also gonna do is have a meter in order to read the amount of electricity that you end up, grabbing from that system. And then all of the circuitry inside of your house is kind of your responsibility. For sort of, it's very much kind of similar to this for sort of non-residential. And so we usually talk about a term as sort of upstream of the meter and downstream of the meter, just kind of make that dividing line between things that the utility is gonna do and things that the customer is ending up having to be responsible for. When we talk about things being make-ready, that means all of the stuff for energization has been installed on kind of one side of the meter. And so utility make-ready means that their distribution network, the transformer, and all of the connections going up to the meter are kind of set in place. And then customer make-ready is all the like circuitry downstream of that. Yeah, and so this particular example is like if you wanted to build out, you know, like a charging station, but it doesn't, that's a, you know, specific end use, it doesn't have to be like this. Generally, the schema, the dividing line for what the utility is gonna be responsible for kind of stops at the meter. Generally, okay, there's like some exceptions in what might constitute sort of responsibility. Sometimes, depending on the project, some of this stuff end user may have to pay for, but that depends on the situation and the project. Okay, any questions about this?
I mean, you pay anyways, indirectly.
Yeah, and we'll talk about that. We have a whole lecture on utility rates, and yeah, we'll get there. You do pay for this stuff, but like, so do a lot of other people. Whereas this stuff, you pay for directly. Oh my gosh, I always get this mixed up, but this is upstream, and this is downstream, right? I think, yes.
Which one's behind the meter or in front of the meter? I don't know.
Yeah, I always get that mixed up too.
Behind the meter is customers.
Yeah, behind the meter is this side, front of meter is this side, yeah. They say behind the meter because that is stuff, anything behind the meter is stuff that the utility doesn't really see. And everything in front of the meter is stuff that the utility will be responsible and have visibility on. Yeah, so when you do like a new connection, what ends up getting deployed, right? You know, you might have some feeder lines, some transformers, meters at your service points. And that doesn't look too different, even for sort of larger class customers. You might have larger transformers, and the sort of the service end is going to be a little bit bigger, but. Yeah. One thing that I'll mention. So sometimes when your request is really, really large, there's some question of like who's responsible for paying, right? And that's something we will talk a lot more in detail. But essentially, it could be the case that you are asking for a lot of electricity, and so there's a lot of like more expensive equipment that needs to get deployed. And so sometimes you may be, when you make these large enough requests, you may be assessed these things known as demand charges. So a demand charge is one of the ways that the utility is going to recoup the costs of deploying some of this type of infrastructure. And that's targeted specifically at sort of large customers of electricity, where essentially you're paying not for the amount of electricity that you're using, but for the infrastructure that's essentially handling that large amount of electricity. And so here you trigger a demand charge if you reach some demand at all during a sort of monthly charge period. And so that's one of the ways that helps pay for some of this stuff, especially the big stuff. And we'll talk more about this with the rate making part of it, of the class later on.
Have there ever been folks who want to do EV charging, like charge like demand charge?
Yes, yeah, that's very common because EV chargers actually have very sort of high electricity draw. And so one of the challenges with deploying, DC fast charging sites is like running into these demand charges, which will make sort of recouping costs for service providers a little bit more challenging. But there have been some, workarounds with that with the legislature and the PUC.
And they don't like distribute that cost equally throughout the neighborhood. It's like on the back of whoever the person is with the EV charger.
Oh, yeah, well, okay, sorry. So if we're talking residential, no. You don't really have demand charges at the residential level. I'm talking like for a public DC fast charging station.
Yeah. That makes sense.
You don't have to pay for like the upgrading your, what is it called? Wall? Not wall.
Service.
Your service panel,
Yeah.
yeah. Yeah, you would be responsible for that, but you personally might not be responsible for if you asked for, a service upgrade and the utility has to put in a bigger transformer to be able to serve you. That cost is going to get spread out to the sort of rate base, usually. Okay, we've talked about this kind of stuff. So in modern networks, some things to think about, limited visibility. So a lot of distribution systems are like passive and unmonitored. And so there's actually even, for utilities to be able to have like insight into what's happening kind of on distribution networks, that might be actually a little bit more limited than people think. And so, more recent measures to help provide that visibility are things like having kind of smart connections with, even at the sort of distribution level to provide insights for utilities. So I've talked about manual switching and restoration, and how you can use sort of smarter equipment to help mitigate the need for this. Integration of DERs, so this is going to require new protections, voltage regulation, and other sort of load forecasting in order to understand the implications of what this is doing sort of at the distribution level. I'll talk more about this in just a second. And then, utilities are moving towards systems where they can sort of understand sort of smarter systems that help them understand what's happening out on the sort of distribution networks, as opposed to, you know, having the sort of more limited visibility. Okay, so this third point I want to touch on really quickly. So, you know, in California, where we have lots of rooftop solar, you know, what does that mean for our distribution system? So just kind of some quick insight, right? So same kind of diagram as before, where we have our primary and secondary distribution separated by these transformers, and that's upstream connected to our high voltage. So you got your house, your end user at the end, right? And so normally we think about electricity flowing down towards the end user, and then you have voltage dropping due to impedance, and all the equipment, right, here and here, all the protection stuff, it's all designed and rated at in a particular way to basically handle what it knows, or I should say what it anticipates the load should be kind of downstream. But now I start adding solar panels, right, to these houses, so that may decrease the current demand, but will also, in some cases, you might want to inject electricity back onto the grid. And so can you do that, right? So yes, so you can do that, but one of the issues is that as you send kind of current back through your distribution system, so that may actually cause voltages to go up on certain parts of your system. So I talked about how like voltage regulators boost your voltage, and in some cases when it only detects kind of current going through. It doesn't care kind of what direction and in what magnitude. Or sorry, it does care about the magnitude, but the direction could be going the opposite way, and so it might be boosting voltages in ways that you don't necessarily want, right? And so what ends up happening is that now you have voltages higher than maybe you had originally rated that system to be, or to handle, because you didn't anticipate this type of thing happening. So end of line voltages can exceed limits, right? And so there's a number of things that utilities try to do to try and mitigate this. Okay, let's talk about economics. Yeah, cost breakdown. This is kind of a quick insight into the way the sort of cash flow works for this. Essentially, when you install these systems, right, the utilities recover the initial investment of this by making all of the people in their territories essentially pay for them. And so you do have kind of these initial capital expenditures and then recovery of that capital expenditure over time. Okay.
Is the x-axis years?
Yes. Yeah. And then, yeah, the sort of cost components on like a unit economics basis look something like this. And so, yeah, you're breaking down all of this, all the material costs over time. Depreciation is all over some set amount of time, and then you're making money back, right, over some period of time. Yeah, as these things are deployed. So the cost for these things can kind of vary wildly. Just to give sort of rough example, so this is from a particular study out of Berkeley where they were looking at kind of rough upgrades to circuitry, and so this can include some of the like conductors, but this is mainly with the sort of transformers, and this gives you yeah, some sense of cost to upgrade as you need more and more sort of electricity on the demand side, what those kind of upgrades look like on a like per kilowatt basis. And so this is your circuitry level, so this is thinking about the wires and transformers, and then substation if you need to upgrade. You're hitting limits of capacity at the substation, so you need more, let's say, transformers at the substation. So those are going to be quite a bit more expensive. Yeah, and you do have some economies of scale, as you can see, if the sort of needs are sort of very large.
This is normalized by kilowatt.
Yeah, by kilowatt. Yeah, so this is, labor cost components. This is maybe about 25% of your total cost. They do this in a kind of interesting breakdown of hours per MBA, but I think more important is just kind of the like relative ratios of these things, right? And so a lot of this labor with the like actual building of the transformer, right? There's little components that add up, but the big ones are kind of design and planning, and then there's this like corporate and management piece. I'm guessing that's just like profits essentially. And to give kind of an aggregate sense of that, so this is over kind of a 20-year span, what the US as a whole spends across all the utilities annually, from 2000 to about 2020, right? So we're on the order of 40 up to $60 billion annually. Yeah, and so a lot of that is in capital investment, and this kind of, there's been kind of a bigger spike even since the sort of COVID years, having to do with, as a kind of direct result of COVID, scarcity in materials and supply of transformers. Yeah, and so actually kind of post 2020, these numbers will get even bigger. But yeah, on the order of tens of billions of dollars a year. Yeah, the economics are a little bit unique. You have very high fixed costs, but low marginal costs, right? Once the transformers are out there, they kind of sit there and do their own thing. Usually you don't require much maintenance, unless your transformer is kind of subject to unusual conditions that you weren't expecting. Usually you don't need to do much once you've kind of deployed them. So capital investment in the poles, wires, transformers, and labor is actually a big one, but actually not a huge amount of energy is needed. Very sensitive to customer density, right? So think about a distribution network serving a really high density area. Maybe, you're thinking like a density like San Francisco, right? Where you have high population density and lots of customers using it. In those contexts, you have kind of this low cost per kilowatt hour, dense load, shorter runs for a lot of your conduit. Whereas in rural contexts, you might have much higher costs per kilowatt hour. You might need long feeders to serve, someone who's, their houses might be kind of spread out over much larger geographies, and you're going to have a lot fewer customers. And so there is some question about cost allocation and who should pay, and that is a age-old question in kind of the electricity system. Yeah, so there's no wholesale market for these kind of systems. So energy passes through, and so the economics mainly focus on infrastructure and the delivery of the service, but not from energy procurements, right, for distribution systems. And one big worry is that there are a lot of like monopoly characteristics of this kind of system. The infrastructure is pretty unique, and so you arguably would want to have regulation to ensure kind of fair cost recovery. Otherwise, you know, I might want to just charge whatever, some exorbitant amount to customers for that transformer, because you might be the only game in town to provide that sort of equipment. And so, yeah, this part is also maybe heavily debated in some ways. Yeah.
What do you mean by the energy is passed through?
So unlike generation, there isn't really the distribution system doesn't operate in like a sort of market mechanism, right? And so people aren't like bidding money to like use the wires, right? Energy kind of just goes through the wires as it's kind of demanded, and it's not based off of like, let me pay more or less amounts of money for like using the wires. And so there's kind of more of a fixed cost to the delivery as opposed to a kind of market-based demand cost on the delivery.
Okay.
All right. So the economics piece touches into some of that rate making that we're going to talk about later. And so the first thing that I kind of want to introduce here as a concept is this idea of rate basing. And so if we're not, you know, paying for the distribution system via some kind of like market mechanism based on demand, right? How is the like capital that I was just talking about, all that capital investment recovered by the utilities that are installing this distribution infrastructure? And the way that they do this is through what is known as rate basing. So it is the process by which a utility earns a return on its capital investments. And so basically, I install all this distribution infrastructure and I say, okay, everybody basically is going to have to pay for it. And there is this equation that kind of describes all this stuff. So rate base multiplied by your rate of return plus your O&M and depreciation and taxes, so all of your other sort of costs. That is, the sum of all of that is known as your revenue requirement. And that revenue requirement is kind of the key piece here. This is the money that a utility is allowed to collect from its customers. So you ask, okay, why is my electricity rate, set at the rate that it is? This part of that electricity bill, is essentially derived from this equation, right? And so this takes into account essentially all of those capital investments plus all of these other costs rolled up into one big sum, and then that money is divided out essentially across all the customers for them to collect. The rate of return itself, right? So this is on top of the actual costs, this is like what the utility will profit, will gain in profit. That's set by regulators, typically on the order of like 8 to, well, I would say even higher, maybe 8 to 12%. And so that's a way to balance the sort of financial health of the utility with customer protection, right? And so the customer protection piece is like saying, okay, we will protect you from the utility charging a onerous amount of money relative to what they spent on all of that capital infrastructure.
That's PUC.
Yes, the PUC, the Public Utilities Commission. And we're gonna talk a lot more about their kind of role in helping to do this regulation. And so you can see the cost recovery, yeah, so that's on the order of like 7 to 10%. Yeah, so I mentioned the cost kind of skyrocketing in recent years. So this was a shortage in distribution equipment due to COVID disruptions in sort of global manufacturing logistics, right? This wasn't the only industry that kind of suffered from this. At the same time where we actually saw a pretty big increase in demand, right? So electric vehicles, data centers, grid modernization, wildfire mitigation, all of these things are kind of happening at the same time in this backdrop where you have these supply shortages. And so costs were skyrocketing, and you also have big lead times to install some of this stuff, right? And so that was going all the way up to 120 weeks, and so you might have to wait 2 years for a service upgrade. Right, and so remember when I was talking about that whole process of getting something deployed, where were we? Way back over here, right? You have this trigger event, you do the engineering assessment and system design, and you get to this part where you actually need to build and deploy it, and the utility says, sorry, we can't do this for like 2 or 3 years, right? So you can imagine how that might affect everywhere from, a small business that wants to install an EV charger all the way up to, a big entity that wants to put a new data center in place. Yeah, so big effects, big sort of downstream effects of all of this. Yeah. Utilities are unable to complete new service connections and distribution upgrades because of this particular phenomenon. But that has sort of started to come down since 2023, 2024. Congress actually passed specific measures in the CHIP Act, I believe, to help boost domestic manufacturing for some of this stuff that has allowed for a decrease in wait times for the supply. Yeah. Yeah, in kind of the recent years, there's been a whole bunch of new sort of facilities focused on manufacturing of this type of equipment in order to try and keep up with demand. So yeah, it's just kind of a rough look at qualitatively, some of this new stuff that's been developed. Okay, last thing we'll talk about quickly, reliability and resilience. Okay, what is reliability? Right, so this is the ability to deliver electricity consistently within acceptable voltage limits. And so when you have an interruption, that is when you have a loss of service to customers, And you can categorize this as sort of momentary or sustained, depending on the duration of an interruption. And there are a number of different metrics with which we use to measure things like reliability. So SAIDI, System Average Interruption Duration Index. This is kind of how long, on average, a customer may expect to be interrupted over the course of a year. SAFE is the System Average Interruption Frequency Index. This is essentially how many times a customer might expect to get interrupted in a particular year. And then Customer Average Interruption Duration Index. This is an index that looks at the sort of ratio between how long and how many. So it would be essentially telling you how long the average interruption would be that you would experience. Okay, so these are like very common metrics and indices that utilities use to measure the reliability of a system, and you can look up data on what these indices look like in different utility territories. I have some data about this and kind of what this looks like. So across the U.S., for example, you might expect on average in 2016, you were seeing something like a 4-hour duration of interruptions over the course of an entire year, whereas 2017, that went up to 8 hours. And that difference is entirely due to certain major events, right? So this might be like a big earthquake or a hurricane knocking out power for several weeks that would really push up that metric. And then in terms of number of interruptions, on average, something between 1 to 1.5, and that didn't really change between 2016 and 2017. Yeah, and so you can see, like, there are a couple of different ways of slicing and dicing this reliability data. But SAIDI and SAFE are kind of the classic way that these are measured. Okay, and we talked about, right, what causes reliability events. A lot of this is wildlife, but some other things. So extreme weather, wind, storms, you might have contact with vegetation is a common one if the vegetation is not sort of properly managed. Car crashes, right? If you crash into a utility pole and down it, obviously that can lead to some issues. And then resilience measures. So reliability, we're thinking about minimizing outages. Resilience, I would kind of think of this as kind of two things. It's the ability to withstand major events, so major like unplanned things like extreme weather events, wildfires, cyber attacks, as well as the ability to recover kind of quickly. And so what sort of measures have we talked about, right? So undergrounding can avoid some of this stuff, maintenance on vegetation, and then, to recover from major events, things like mobile substations help when certain types of services are down. Like if you have damage at a substation, you can like quickly go in to provide like a temporary relief service through something like this. Also, microgrids. This is one way to create some kind of resiliency where you might have a sort of local independent grid operation that allows you to maintain service when you have when your upstream resources become damaged, right? And so in critical places, like you might think of like a hospital, maybe it's got its own generator, or maybe it's connected independently to a sort of small microgrid system. These are ways that you can be resilient to some of those extreme weather events or other sorts of extreme events that I was mentioning. Okay. Well, there's like a couple slides left, but maybe I'll just pick this stuff up at the beginning next time, and we'll just do a quick review and then talk about some of the sort of policy pieces. But yeah, we're at the end for today, so let's end here. And again, as a reminder, right, next class, that's going to be our field trip visit to the UC Davis substation. I put the instructions online, but apparently we also have an address now that you can Google Maps to. So I'll post that as well. Can you remind me what the address is? And,
Yeah, I'll shoot you an email.
yeah, and I'll post that. I will try and stay out at the gate until maybe like 3:05 or so. So maybe try and come a little bit early just to make sure we can all get there. All right, I will see you guys all on Thursday.